talk a little bit about the definition of work a little bit more. We said that we can add or remove energy using work. So if I went back to, very same example where we had the 3 kilogram object moving at the same speed, we'll do like 2 meters per second, and then, what we said was, okay, we've got some sort of force acting on it. Maybe I don't match the force again, or maybe I'll still call it a 6 Newton force. But in this case, if I'm doing a 6 Newton force, let me actually come up with a number that's going to work well with our initial values here. So I initially have, let's say, 6 joules of kinetic energy by doing 1/2 mv squared. So I'm going to have our force be a 6 Newton force, and we're only going to do it over a distance of 1 meter here. All right, so essentially, if we're figuring out what the work is here, the work done by this is going to be equal to force times distance times cosine theta. Again, theta is 0 here. So it's 6 times 1. We get 6 joules. By the way, force times distance is newtons times meters. And if you work that out, that ends up being kilograms, meters squared per second squared, which is still joules. So newtons times meters is joules here. So we get plus 6 joules of work here. And that's important because what we saw is that the energy increased in a scenario like this. What we want to go back to is possibly something different. You got 3 kilograms here moving at 2 meters per second that way. But now let's apply a 6 Newton force that way in the negative direction. What that's going to do is it's still going to move forward, but what ends up happening is that our force is working against the motion now. So we expect this to slow down. We expect this to lose kinetic energy. What we're doing here is we're applying a force over a distance to remove energy here. So when you calculate the work here, it is negative 6 newtons times 1 meter. And what ends up happening is that we get negative 6 joules of work. Now keep in mind, work is a scalar quantity. All forms of energy are scalar quantities. So we have positive and negative values of work, but it doesn't tell us direction here. If we look at the work energy theorem here, let's say that we have kinetic energy, we do some work, and we have a new kinetic energy because we change that energy with the work. We'll do the work energy theorem here. This is our conservation of energy expression here. And what we have is we've got 1/2 times 3 times 2 squared, which is 6 joules. And then we have negative 6 as our force. The displacement is 1. Cosine 0 is 1 as well. And then that would give us our final kinetic energy. And if you happen to look here, this ends up being 6, and this ends up being negative 6. So we start out with 6 joules of energy, but we're going to remove 6 joules of energy. And so that means our final kinetic energy ends up being 0 joules. So what this force is going to do is it's going to remove all the kinetic energy from our object, and our object's going to end up sitting here at 0 meters per second once we do that. So we can use energy to work to remove energy from the system. So that's what your negative value means. That means that energy was removed as opposed to added to the system. So when you have a positive value of work, we add energy. When you have a negative value of work, we remove energy. And you got to keep in mind that there's a few permutations here with respect to work. So you just saw that we had a force applied over a distance there. Those are both positive values which led your work to be positive. So something like that would add energy. But we just now also saw a negative force still applied over this distance, negative and positive values, ends up giving you a negative value for your work. And you got to be careful because we don't really know anything about direction looking at these quantities here. For example, if your object was moving in that direction and you applied a force in that direction, it would be over that distance there. Both of these are negative. So when you calculate your work here, you'd have a negative times a negative. You would still get a positive value of work here. So a scenario like this, where both things are pointed to the left, will still end up adding energy to the system. And likewise, if your object's already moving this way, to the left, but you apply a force that way against the motion, well, it's going to continue to move that way, but it's going to be slowing down. You got a positive and negative value for force and distance respectively. multiply them out, you're going to get a negative value of work. So this scenario removes energy, much like this scenario where we're moving to the right. And you have your two scenarios that add energy as well. So you got to think about the direction of both F and D and your original motion in order to really determine what's going to happen.